Let's say you've studied Lesson 8 on image optimization, and you've tried several things, but you still think your AFM images are being perturbed. In this lesson, Lesson 9, we'll talk about different kinds of perturbations and how they might be fixed. Broadly speaking, I'd say there are 4 different types of perturbations: mechanical, electromagnetic, environmental, and design. I'll take them one at a time and give you examples of each and what you might be able to do about them. Mechanical. Here is a tall building with floors. You do not want to put your AFM on the top floor. Whereas we don't notice the building swaying, the AFM does. So the closer you are to the basement, the better. Now, sometimes basements just aren't accessible, sometimes they're dirty, sometimes people are already there, so you might have to go up a floor or two. And if you do, don't put your AFM in the middle of the floor. Why? Because the middle of the floor vibrates up and down, whereas, so not there, but as close to a wall or a corner as possible, near to a major support structure. So basements are good, lower floors are good, but you'll still need to vibrationally isolate it as best as possible. If you go for the expense of a vibrationally isolated floor, that's great. But less expensive options are air tables and bungee cords. You can hang bungee cords from the ceiling and have a platform. What you're looking for is a resonant frequency of that system of about a hertz or lower. Building vibrations are on the order of 10 to 100 hertz, so if you come in much lower than that, that would be good. Most of the time, however, people buy air tables. They're a little bit more convenient to work with. What you want to watch out for is if in your ceiling you have a vent with air coming down, and you don't want to have air blowing all over your AFM. And not only air, but just acoustic vibrations in general. You need to shield it from the air flow from a door, from a hallway, from people talking. That shielding should also not only be mechanical acoustic, but also be electromagnetic, i.e. you should have some foil in there and ground that foil. Electromagnetic. Here's your air table on a vibrationally isolating slab in a basement. Here's your AFM. Here are your lines between your instrument head and electronics. And here's your line to the power outlet on the wall. So, as I suggested in the last slide, we want to have the AFM electromagnetically shielded, i.e. all this enclosure around it to be grounded, and that helps protect it from radiation, electromagnetic radiation. It's all over a lab. The lights, they tend to give off 60 hertz or 50 hertz radiation that's easily picked up by the instrument. Should make sure that the casing is grounded as well. And the power that comes in to your lab is sometimes not so nice and clean like a sine wave. Sometimes it's got all sorts of noise on top of it. So that's not a good start. So I recommend buying a power conditioner to take that line voltage and clean it up. You can get some with batteries, such that if the power goes off, you've got a few minutes to return your AFM to a safe condition. So let's see, grounding, shielding, power conditioner, dedicated line. Yes, dedicated line. The instruments in the hallway that might be sharing the same power line as your AFM, some of them might require a lot of power to get started. So there are frequently power surges if you're sharing electrical power with other instruments. So it's best to have your AFMs on their own dedicated line. Environmental. You should think about the environment that you're creating for your AFM. You want a stable temperature. A temperature change that's small to us can be very big to AFM. Just a few microns of drift, well, you can detect that with AFM. So have some means of keeping the temperature in your lab stable. That's another reason that basements are good. Basements typically don't have windows. Windows allow sunlight in, and that causes a higher thermal cycle throughout the day. Pay attention to your air quality, i.e. the dust. Fortunately here, there are inexpensive solutions for keeping your lab fairly free of dust. You can put sticky mats at the entrance. You can require people to wear booties on their shoes. You can place air filters over the air inlet and air outlet. In this way, you can prevent the buildup of dust, which, of course, little particles of dust look like mountains in an AFM image. You should pay attention to humidity. A target of 40% relative humidity is good. If humidity is too low, there's possibility of static buildup. Electrical forces are huge in AFM and very hard to control. If the humidity is really high, water films tend to form on many surfaces. This affects the adhesion between the tip and the sample. And finally, design. Most people don't think of design as a perturbation per se, but I include it here because sometimes people want their AFMs to do everything, and that's not realistic. So, example. One of the AFMs I have is designed like this. It's got a big, massive, stiff granite arm and a stiff granite plate. And here's where we put the scan head with the cantilever. And the reason why it's done this way is because now we can have a motorized stage down here with an 8-inch silicon wafer there. That motorized stage allows you to go to several places on that silicon wafer and check for roughness. But the problem is that even though these pieces are big and stiff and you don't expect them to vibrate, again, we have an extraordinarily sensitive instrument here. And this arm wiggles up and down like that. So much so that it would be unrealistic of me to expect better than 2 angstroms of noise. So if I really wanted to do very, very high resolution imaging with very low noise, I would just have to start all over and look for another kind of AFM to do that particular kind of imaging, or just design one myself. Now these days, that's much less practical. There's such a wide range of choices of AFMs on the market. And in addition to mechanical design, also be wary of what you're buying when you buy an AFM in terms of the electrical design. Some manufacturers will choose an electrical frequency range to be narrow as a way of limiting noise But you might require certain measurements to be done at high frequencies that require a higher range of frequencies to be collected. In summary, then, there are three types of perturbations about which you can make some modifications and maybe help your imaging. And about 3 times a year, I schedule some time to go down into my lab and check for all these types of perturbations, tighten loose parts to ward off mechanical vibrations, check that everything is grounded, make sure my air filters are clean, etc., etc. But fortunately, there's not much you can do about a poor design choice other than designing an AFM yourself or buying a complementary instrument, one that has a slightly different set of capabilities as your existing instrument. The good news is that these days there are plenty of choice on the AFM market, and you can probably find something that matches your needs.